Okay, any questions? So I want to do a couple of examples and continue our discussion. So what we have seen is, remember I did a problem in the last lecture. You have a ball of charge that is rotating. Okay? And as a result, we found out that there's a K. And of course, it is sigma V. We wrote an expression for this. Sigma is easy enough. Q over 4 pi r squared. V is r omega, but remember, it is r sine theta omega, because this is rotating with an angular velocity of omega. I've only written the magnitude thus far, and if you want to make it vectorial, you put phi hat. Okay? The current and so I can write this as di, just in magnitude at least. If you want to put vectorially, you can, but let me write it in all its components. 4 pi r squared, r sine theta omega. Now, so this is sigma. This is V, and then dl perp, which is r d theta. So there's another problem that I wish to do. I will do it using a trick, same as in Calculus 2 or Calculus 2, I think. When you integrate over surfaces, you do a washer method, right? We'll use that. It saves you a lot of trouble. But then you will have seen the complete calculation, and hidden in that calculation is the exact way of doing it, and I will let you go through that. So let me explain. So the problem that I'm going to do is, I just want to tell you the problem number. The question itself is, what is the B here? At the origin. What's the magnetic field created by this rotating ball? So let me look at the problem number. It's 512. Now, first of all, you might say, whoa, it's a sphere, it's rotating, it's a center, magnetic field is 0. Why wouldn't it be 0? Why could it have a preferred direction? You're spinning it in a preferred direction. So if it were just charges, the electric field would be 0, but now there's a preferred direction. Okay, to do this problem, like I said, I'm going to cheat. So the cheat is so that you read up the following example. I did example 5.5 in class. You have to do example 5.6. So what is example 5.6? Well, let me explain. Example 5.6. So here is 5.6. So you have a circular current. And the question is, what's the magnetic field over here? And the distance is Z. This is R, and this is Z. First of all, what would be the direction of this magnetic field? Well, so let's look at this. Recall Biot-Savart's law. B equals mu 0 over 4 pi I dl prime. So the direction itself is determined by this. Okay? So if I look over here, this is dl prime. And r prime, separation vector, is this. And so, if I do, let's make sure, yeah, this is going to come out like this. So the magnetic field is going to be this. And as I go through the circle, the magnetic field is going to do that, from contribution from each small segment. But in the sweep, it is symmetric, so only the z component will survive. So B is actually Bz in the z hat direction. And here, when you do this integral, you'll simply read the example from the textbook. Turns out the value, the actual expression you get is mu 0 I over 2 r squared plus z squared over 3/2. This is interesting, huh? There's something happening to the magnetic field. Now, if I saw this expression for electric field for a ring, without knowing, some different constant, I would immediately say this is not true, because infinitely far away, it should look like this ring should look like a point, and it should be 1 over z squared. Look at this. This is 1 over z cubed. Magnetic fields are falling off a little faster. We'll see, there's no monopole term in the magnetic field. Yeah? There's no isolated magnetic charge. You don't have a plus magnet and a minus magnet. Every magnet will have a plus and minus pair. Because of that, there's no monopole term. And in the multipole expansion, if you recall, the first term is the monopole term, then the dipole term, and the dipole falls off faster than the monopole. And there it is. Yeah? NASA spent billions of dollars looking for the magnetic monopole, but because it was predicted by certain advanced theories. Turns out we couldn't find it. So we're still back to...
Not yet.
Not yet. Well, if we do, yeah. Okay, now what has this got to do with that? Well, I'm trying to, first of all, I don't know how to do this one, because Biot-Savart's law is just a current. I'll have to give the generalized expression. But I do know how to cheat. What I'll do here is look at this ring. And consider the sphere to be a stack of rings. Except we have to make sure we flip things down again. You play the same game. The magnetic field here is this way. If you look over here, the magnetic field is also going to point that way. It doesn't point that way, downward. You can see. So, no, that shouldn't happen. How do I do this? So if I had a...
point up, yeah.
I'm sorry?
It's supposed to point, everything's supposed to point up?
Yeah.
Yeah, because if one's still down and then this one's still look up, in that direction. Like that would be the resulting up, and then going around.
Would add up to be up?
Yeah.
Yeah. So you have to convince yourself that is true. Is that clear to you?
Basically.
So, all right. So what we'll do is start with this one and make the necessary changes. We know it's going to be in the z direction. And then we have to make few changes. Well, you know mu0 and 2 will not do anything. And now if this is theta, as usual, and this is r, this is r sine theta. So we have to make the transformation. R goes to r sine theta, and z goes to z cosine theta. I goes to integral of di, because there are many such currents. Yeah? And that is nothing more than integral of k r d theta. Not I equal to, but I goes to that. And then you integrate theta from 0 to pi. Chip, is that clear? So in this case, in that problem, this is r. So the equivalent would be this. Here r is the radius of the circle. So for each current, each loop, if you will, it's only r sine theta. And z is this distance. Again, in our coordinate system, z is r cosine theta. And as you vary theta, it goes from r to minus r.
The only thing
I'm sorry?
The only thing I'm not sure about is, I know we went over this, but why is it the z direction?
Oh, yeah. So look at this. This is my separation vector. So this is better. So this is part of my loop. Okay, and I'm somewhere over here. So this is the current. And this is my separation vector. So when I do dl cross that, I will get this. Right? Like pointing up, but this way. See? Let me bring that over here. So look, this is my separation vector. So then I take it and I bring it over here. dl cross r hat.
And you get rotated all around.
And-
Yeah.
right.
The only turn that survives.
So then you're going to rotate it all around. That's exactly what Martin said. Then it's going to do this.
Oh, okay. Yeah.
So all the other components cancel off.
Got it.
The only thing that survives is.
Yeah.
Okay. So because I need space, I'm going to erase that. But are the transformations clear? Okay. In that case, let's do this carefully. Mu0 over 2. R squared is r squared sine squared theta, because it is r sine theta. This becomes r squared sine squared theta plus r squared cosine squared theta, very convenient, over 3 over 2. We don't get so lucky so often. Now comes the di part. So I have, well, q over 4 pi r squared r sine theta omega r Are we good? And as we go through the entire sphere, we get that. Sigma, this is sigma. This is V. This is dl perp. I goes to K dl perp. Remember, I is, or di is K dl perp, sigma v dl perp. So let's collect all the things. I know this very easily. I know mu0. I know there's a q. I know there's an omega. There's a 2 here. There's a 4 here. That's 8 pi. How many r's? This is r squared. So it's r cubed. R to the 5th. So it's 1 over r. Yeah, 1 over r.
So the reason we're only going half the circle is because for every...
We're not going half the circle. We're going from 0 to pi. Theta only goes from 0 to pi. Phi goes from 0 to 2 pi.
But for every theta, we have a complete range.
Correct. Yeah, so in spherical coordinate system, r theta phi, r goes from 0 to infinity, phi goes from 0 to 2 pi, theta goes from 0 to pi. This one I looked up. There's no way I'm going to do this off the cuff. It's 4/3. You can verify this. And what's the answer? mu0 q omega 6, right? 6 pi r. We can even make this fancy. Yeah? Any questions? Okay. Leave that. I'll throw this one in the exam to do the same problem using the new expression that I'm going to write. So this is clearly true if there's a loop current. Okay, so let me write this here again. But what happens if it is a surface current? Well, it's simple. One doesn't follow from the other. You have to experimentally verify this is true. This becomes a dA. And so you bring a surface current cross r hat. Yeah? And can you guess by analogy, what if you're talking about currents in space? Now, mind you, all this means steady state, huh? The current is steady. What do you think this will become? These two will obviously get modified.
J and eta.
J, yeah. And these are all primes. You're integrating actually where the sources are. So using this second formula, you can do this exact same problem. Yeah? And I would like for you to verify that. That is, this is the, it'll be on the exam. So by that I mean you can start working it out in preparation. Okay, now let's see who remembers. First one is 0, and when I say 0, it really is a 0 vector. This one is what?
Rho epsilon.
Correct, charge density over epsilon naught. And we know from Helmholtz's theorem that if you know the divergence and the curl of a vector field, the electric field is uniquely determined. And because of that, we have found all sorts of ways of computing electric field by using electric potential, by uniqueness theorem, all sorts of results nicely followed. So then, the question arises, so this is electrostatics. I must, okay? So at least in the context of, because we don't know electrodynamics yet, magnetostatics. What is this? And
The first one's 0.
because,
There's no magnetic modifier.
well, correct. So it's the flip. So here the curl is non-zero. If the curl were 0 too, then the magnetic field would be trivial. There's no magnetic field in the universe. Okay. Now again, this is magnetostatics. One of the requirements of magnetostatics is d rho dt is 0. There may be charges flowing, but the charges flowing is constant in time. That also implies that divergence of J is what? 0, because of continuity equation. D rho dt plus divergence of J is 0. So if one of them is 0, the other is 0. Okay, fine. Well, let me give you the answer. That's what it's going to end up being, mu naught times the vector J, the current density vector J. So we will take this expression, the most general expression, because surface currents and line currents can be obtained from this using delta functions if you want. This is the most general expression. And what we'll do is we'll take the divergence and curl on both sides. Okay. Now, divergence of B. B is a function of some x, y, and z. So divergence is with respect to x, y, and z. That's equal to mu 0 over 4 pi divergence of J, and really J, I should put a prime here, but these are sources. Okay, Okay, these are only dependent on x prime, y prime, z prime, not x, y, and z. So let me make that explicitly clear. Separation vector has both x and x prime and y prime. I know that's been a while, so let me, and this is d tau prime. See, separation vector is x minus x prime, x hat plus y minus y prime, y hat plus z minus z prime, z hat. It has both the primed and unprimed variable. Okay, so whenever you see something like this, you immediately look at the inside cover of your textbook and see which rule it applies to. So let me do exactly that. And divergence of the cross product.
Product 6.
Correct. So divergence of A cross B, so A cross B equals B dot curl of A minus A dot curl of B. Okay? Well, this B has got nothing to do with our B. This is just general expression. So let's do divergence B. What are the two terms? So I'll group these guys together. Okay? So then I have dot curl of J prime minus, and of course I have to put dt there, A, which is J prime, of dot curl of You know what this is? This is just vector analysis just over and over again. This is not really difficult, but just keeping track of the argument. It looks a little easier when it's a prepared talk. Otherwise, every time I have to lecture, I have to go through the notes and make sure that the steps are careful. It's not that difficult. It's not conceptually that difficult. But you just have to be careful. We want the answer to be 0, so obviously this is going to be 0, that's going to be 0. And it's going to be immediate. But I should have recalled a few other things. So let me continue my recall here. Gradient of, what is that? And divergence of this guy, because you created a vector, and the divergence of is a delta function. So this is the gradient of something. But this is the gradient of not something, it's gradient of this. Yeah, curl of the gradient is 0. This is unprimed variable. This one has only primed variables. And therefore, this is 0. And as desired, you can look around for monopoles all you like.
So say that one again. for the curl of J prime?
Yeah, so J prime, I don't care what it is. The x component is x prime, y prime, z prime, x hat. These are all primed variables. You're integrating over the current. This is where the field is being evaluated. Look, you're taking it's with respect to x, y, z. So there are no x, y, z here at all. It's like the dl prime. Has nothing to do with the field point. So in that sort of that circle example, and you computed the magnetic field here along the z-axis. You're taking the divergence of this magnetic field. So you're looking at how the magnetic field changes around here. But in each of these integral, there's this ring. And the ring only goes around the ring. You can change anything you want. The ring is the ring. Same way. This one has no x, y, z variables. So the divergence of B is 0 as required. Now let's look at curl of J. This is the answer we should get. Once we get to this answer, I'll stop and the other terms, let's say it goes to 0. And you can go through the textbook. The argument is simple, but the non-zero part is the interesting part. So again, recall that there are no, J has no x, y, and z. So curl of B is equal to mu0 over 4 pi curl of this way, d tau prime, which curl of A cross B. This is product 8. Product rule 8, if you have your textbook. It has 4 terms in it, but whenever you see a gradient with respect to A, that term is 0. Because A is J prime over here. Correct? And it won't see the derivatives. So, well, let's look at one by one. Chip, you should have the equation in front of you, otherwise you'll have to take this on faith. Will the first term appear? See, this is like my A, and this is my B. The first term has the gradient operator acting on A. That means gradient operator acting on J. That won't appear. Yeah? The second will appear, and the third will appear. Fourth will not appear. So because the third is positive, let me write third first. So it is, and please make sure that it is correct. Divergence of minus the second one, right? Correct. J acting on B. B is what? Yeah? This will get us what we want. Yeah? This guy is 4 pi let me be very specific. So when you integrate over all prime variables, you'll get it only where you'll get the value of this function evaluated at this point. The 4 pi's will cancel, and I would get mu0 times j. Yeah? Obviously, what am I, if that is the answer, we know that's the answer, what must be true? This must go to 0. It's not very hard to see. It's clearly spelled out in the book. You know the story. Now you're just filling out 3 lines of algebra. If you have questions, you can come and ask. Yeah? Again, don't let this weigh you down. These are just vector identities. Whenever you need to be careful, you go through the textbook and make sure that the argument follows. Or conversely, if you know the result, you know which term should go to 0, which term shouldn't go to 0. Work hard till the 0 terms go to 0. So the equations of magnetostatics now become so just as there is Gauss's law, where we use the divergence of electric field, we can use a similar Stokes version of that, and it's called Ampere's law. So if I do del cross B dot dA, so I'll take an area like this, and I'll compute the curl of B and integrate it along this area. So this is, for example, the dA element is perpendicular to the surface. Okay? And you integrate it. But if you recall Stokes' theorem, what is this equal to? That's you just take the dot product of B along the boundary of the surface, and then you integrate. It's a one-dimensional integral. Well, on the other hand, this is equal to mu naught J dot dA. This is the current enclosed. Remember? Just locally, let's not. If you want. That's where it comes from. Ampere's law says B dot dl equals mu 0. Closed. What symbol does Griffiths use? E and C. I didn't write this, very carefully. Divergence of E was what? E dot dA. We didn't write it that way. E dot dA is Q, right? It's the parallel to that. But this is Ampere's law. Just like this is used for Gauss's theorem to easily calculate the electric field, in this case, we'll use Ampere's law to calculate magnetic fields in simple symmetric cases. Yeah? But that is a story for another